In this video, we'll briefly discuss section 6.7, but 6.7 won't come up on any tests, any quizzes. This is just going to be some very quick information, just so you've heard of the hyperbolic trig functions. We mentioned in the 6.5 video, some students go into differential equations after calculus, especially a lot of the engineers. The hyperbolic trig functions do come up there from time to time. So again, not that there's any test material or any homework from this section, but I wanted to take a few minutes to just discuss these functions for your information. And then after that, I want to take a little time and do some general integration review. So we move into chapter 7. It's all about higher level techniques of integration. But before we can get to those higher level techniques, we have to make sure we have all of our basics. And the new functions, log, e, inverse tan, inverse sine, all of those are going to continue to come up throughout the semester. So first things first, again, just a little bit of information on the hyperbolic trig functions. We have hyperbolic sine x. Some people actually read that synth x, almost like that's a th, synth x. More people in my experience tend to just call it hyperbolic sine. And we also have hyperbolic cosine, cosh x, hyperbolic tangent, tanth x. I could keep going. Hyperbolic cosecant, hyperbolic secant, hyperbolic cotangent. But first things first, what are these functions? Well, going backwards for a quick moment, section 6.5, we learned all about exponential growth and decay, and we started to see a little bit more about how important the e to the x function really is. It really comes up in a lot of different applications where we're applying mathematics to these different situations. E comes up a lot. But it's not always e to the x, e to the minus x if we have any kind of exponential decay, but also combinations of e's. And that's where these functions are based on. Hyperbolic sine is actually this combination of e functions. E to the x minus e to the minus x all over 2. That strange combination, well again, it seems strange, but it actually still comes up quite a bit. If I remember correctly, a lot of like your power cables, the way the angle, the curve that goes with the angle that those make as they lie from cable to cable, from post to post, that they actually follow this curve. And there's other connections as well. So again, these nice combinations of e's. For hyperbolic cosine, it's almost the same thing, except that's a plus e to the minus x over 2. Now you might be curious, where do the trig functions come in? Okay, it's one thing to say that these combinations come up fairly frequently, but it's another thing to say that we're going to give it its own specific function, and why would we call that function something so similar to our regular trig functions? Again, we could keep going on and on about all of this information, but just some quick information. Any problems that deal with these functions, you could always just substitute these. Hyperbolic tangent is hyperbolic sine over hyperbolic cosine. Just be careful here. Make sure the h, like right here, the h is a part of the sin, not a part of the variable x. But now having that basic definition, so hyperbolic tangent is essentially defined the same way tangent is in terms of the primary trig functions, but I could keep going. I could literally take this divided by this. That's the real definition of hyperbolic tangent. For hyperbolic cosecant, 1 over hyperbolic sine, so flip this. So we could keep going with those basic definitions, but realize, why do we call them the hyperbolic trig functions? Well, it's kind of funny, but they actually have a lot of the same properties as the regular trig functions. If you took the derivative of hyperbolic sine, take the derivative here. The derivative here is exactly the same. Here you get an extra negative, kick that in front, it's a positive. And the derivative of hyperbolic sine is hyperbolic cosine. But it's not always perfect. The derivative of cosine is negative sine, but if you take the derivative of hyperbolic cosine, you actually get hyperbolic sine. You don't get an extra negative. And again, there are other similarities. We can keep going with the reciprocal trig functions and similar combinations and similar types of things happen. We have the Pythagorean trig identity, cosine squared plus sine squared equals 1. Well, here it's hyperbolic cosine squared minus hyperbolic sine squared equals 1. So again, there's a lot of similar properties, but that's all I want to say. Just very, very quick, looking at them. Oh, even more basic, I should have started with this. What is hyperbolic sine of 0? Well, sine of 0 is 0, and nice coincidence, that same thing happens with hyperbolic sine. Plug 0 in here, e to the 0 minus e to the negative 0. That's 1 minus 1 all over 2. That equals 0. Hyperbolic cosine of 0 equals 1, the same way cosine of 0 equals 1. And again, everything I'm saying we could confirm by going back to these original definitions, whether they're the basics of the function, the pre-calculus. If we wanted to study limits or anything like that, we'd study by looking at these. As x goes to infinity, this goes to infinity, that goes to 0. This goes to infinity, that goes to 0. As x goes to negative infinity, that goes to 0. This would now go to infinity, but I've got 0 minus infinity, so we get negative infinity. So again, anything we did with these new functions, we'd really actually solve getting our feet wet by going back and using these original definitions. So that's it. That's all I wanted to say about hyperbolic trig. Like I said, just a little bit of quick for your information. If it ever comes up in a later math class, you know where to go. And you know it's really, you'd be using these functions, but you'd really be thinking in terms of these. Okay. So now, this is not a complete review of integration. This is really just a review of integration from the new stuff that we found in Chapter 6. So before I start getting any problems and any reminders, let's just get a nice little list. I'm not going to go through all the stuff we had at the beginning of the class. I'm just going to go to the new stuff. We had a new function e to the u that had derivative e to the u du. We had a new function log of u that had a derivative 1 over u du, or u to the minus 1 du for the antiderivative purposes. For antiderivative, I need my absolute value. Once we did this, we found out that we could now find the antiderivatives of some of our other trig functions. We figured out the anti of tan of u is log of secant u, and the anti of secant u is log of secant u plus tan u. And those were tough, but we proved those, so now we can just use them. And now the last two, new function, inverse sine of u, has this as its derivative, 1 over the radical 1 minus u squared. We mentioned in the 6.6 video, be careful, u squared minus 1 is entirely different than 1 minus u squared. So there's inverse sine. And then inverse tangent, 1 over u squared plus 1 du. Some people have it 1 plus u squared. The addition, here that's big difference. U squared minus 1 is very different than 1 minus u squared. But u squared plus 1, 1 plus u squared, that's all the same thing. So again, little things for yourself. Some people need to make that extra note. This equals u to the minus 1 du, because even when they see things like this, they're so tempted to just bring it up as a u or an x to the negative 1. And they try and use power rule, but power rule doesn't apply. For this one, again, if you need that reminder that this is the same thing as 1 over 1 plus u squared, you should include that. Because now, the whole big picture purpose of integration is really, do you know something that has that as a derivative? So even if something looks ugly and complicated, if we know something that has that as its derivative, it's actually not bad. So let's jump right in. Let's evaluate, just like we've been doing a lot of. I'm really going to focus on just the antiderivative. So all I'm going to set up here are indefinite integrals. And let's start off with one that looks a little messy. it's got all these pieces, and it's an e function and an x in the denominator and a radical with something inside and this bigger piece in the denominator. And if we're not clear on our basics, this could be a nightmare. But what we should see, even though these pieces look ugly, they're still 4 pieces separated by addition, subtraction. This first piece couldn't be any better. It's that plain simple e to the x. So that e to the x dx is already a perfect match. Don't let the 4 bother you. The 4 just pushes along, and the anti of e to the x is itself. But now, and you know, I did that quickly, but just like derivatives, we should always check what's our status and is everything ready before we jump in and take the anti. And that's where maybe you're not quite clear, and so some people may, again, they do that rewrite. But even if you do that rewrite, that is not power rule. That is still taking us right back to here. So some of us, that's the rewrite they see. Others, they think of it more this way. They kick that 10 out in front, so the minus 10 pushes along, and now they see it even more directly. The 1 over x dx is the 1 over u du has an anti-log of u, which in this case would be log of x. And don't forget your absolute value. And the same exact thing with these next two. Both of these look ugly. Both of these have division. And it's not just flip it up like we did here. Even if you do that, that doesn't make any difference. Make that the 1/2 power, bring it up. You're still in a messy situation. And by doing all this rewrite work, you're probably getting yourself more tempted to make a USub. If this is u, then you've got a u to the n power, and think of this as power rule, but that's not going to work. And the reason it's not going to work is because that is already a known antiderivative. That has to stand out. Don't let the 4 bother you, just like that 10 shouldn't bother us. Kick the 4 out in front. 4 times 1 over radical 1 minus x squared. That is a perfect match to this right here. So this is plus 4 inverse sine x. And the same thing here with this one. Plus 7 over 1 plus x squared, same as x squared plus 1. It's got that perfect matching denominator. That's not a variable in the numerator. Same thing here, it's not a variable in the numerator. That extra multiplier, that extra coefficient, kick out in front, push along. Same thing here, I just need to squeeze in right here. So that plus 7 pushes along, and then I get inverse tan x plus c. So again, looked really ugly, had lots of stuff going on there, but really, really not that bad as long as we know our new list. I mean, you could really even go back to that first review of integration that we did in our basic review, and we talked about this with basic trig functions. You know, if I did number 2 and I had secant squared theta minus 4 cosecant theta cotan theta d theta, I mean, initially, just looking at that, there's nothing new here, by the way. This is all Calc 1. And there's nothing that even needs to be adjusted. That looks ugly. A function being squared has that sense of inner, outer. Here, there's multiplication of 2 trig functions. So it feels like there's so much temptation on what should be done, but these are both known trig antiderivatives. What function has a derivative secant squared? Tangent has that as a derivative. So therefore, tangent is the antiderivative. Here, just don't let the minus fool you. How do you get a derivative of cosecant cotangent? Well, cosecant has a derivative of negative cosecant cotangent. So plus 4 pushes along cosecant theta plus c. And just another very quick reminder from the quiz on volume, just a couple of you are still a little shaky with your notation. As soon as you take the antiderivative, that's when the integral symbol and your d, dx, d theta, whatever it is, they drop when you take the antiderivative. And at the end of that antiderivative, that's where you get either the plus c or the bar, depending on whether it's definite or indefinite. But it's bad habit. You should not have integral tan theta plus 4 cosecant. That is a terrible, terrible habit. So couple of you got away with that on the volume quiz, but let's really try and break that habit. Use the notation properly. Okay, so now that I've got this whole list up here, now we have new ideas for USubs. So all these previous ideas, they still apply, but we have to recognize when they apply, when they don't. Okay? So let's jump in, let's do some more. And I'm not saying anything new. Everything has been said, whether it was in the 6.2 video, the 6.4 video, the 6.6 video, all these ideas have been covered. It's just trying to see them all together. What is the real purpose of antiderivatives? Find a function that if you take the derivative, you go right back to where you started. Take the derivative here, and we jump right back to where we were a moment ago. Absolute confirmation, this is the correct antiderivative. So, our basic steps. We have nothing set in stone, but what we basically look for is, number one, are we in a good situation? And that's, are there multiple terms? How are those terms connected? Hopefully they're connected by addition, subtraction. Do we already have known trig antiderivatives like we did here? So again, both of these were already in those good situations. But if we're not in a good situation, here we see multiplication, here we see inner outer. But those are troubling if they're not already known trig antiderivatives. And that's where we go to step 2 and we start thinking about appropriate USubs. But now we've added a bunch with our USubs. We could still think about just trying U, and there could be some guess and check a little bit, but hopefully we're already starting to get better habits. U as the inner function was kind of our old go-to from Calc 1. But now we start to see, well, if there's an E, U as the exponent might work. If there's a fraction, U as the denominator might work. If we have basic trigs, tan and secant, U as the inner piece might work. If we have these particular forms, we've seen about trying to make our U so that this exact piece is U squared. This exact piece is U squared. So let's practice those things. So let's jump, still evaluating the integrals. And now number 3, let's look at the integral 8x over radical 1 minus x squared. Now be careful, everybody. We've literally just finished this. We focused on the denominator and pointed out how cleanly that moved back to inverse sine. But this and this are very, very different. And you might say, well, Professor, why is this different? Just kick the 8x out in front, and then you get inverse sine x. You can't kick the x out in front. That is, without a doubt, the biggest difference between this piece right here and this piece right here. If this was an 8 over radical 1 minus x squared, we would just kick the 8 out in front, and that's inverse sine x. But that extra x makes all the difference. So now this is not inverse sine. Sorry, right here. That is not a perfect inverse sine. So we have to move on. And now it's like, okay, well, what else do I see? Well, I see this messy division. I can't divide it or clean any of that up. So what can I do? Well, I can try a USub. And my basic USub, I try U is what's inside. That's inside. This is 1 minus x squared to the 1/2 power. So that has that inner outer layer. We'll try U as the inside. If we've been establishing good habits with our derivatives, with the du part, we should feel pretty good about this. That extra x was the problem, and that x from the derivative is what we're hoping will cancel with it. So this makes me feel like this is going to work. But again, for some of us, we still don't get that ultimate confirmation until we plug in. So for the moment, 8x is hanging out. This is now u to the 1/2 power. Dx gets replaced with du over minus 2x. And as we said, it is perfect. The x's cancel. The numbers reduce, but that's just a little bonus. Whether that was a 9 over a negative 2, no big deal. Now we can just kick those out in front, but the variables canceled. But this is another good reminder, just because we're moving on and have some new functions, we still have to remember our basics. This is good. we had ugly division and an inner-outer layer, and now we got rid of the inner-outer, but now we still have a little very basic division, but we could fix that by bringing this to the numerator, and now this is just some nice simple power rule. Add 1 to the exponent, I get u to the positive 1/2. Dividing by 1/2, dividing by 1/2 is times the 2 over 1. I get my plus c, so I get minus 8, 1 minus x squared to the 1/2 power plus c. Or the square root if you prefer. Good answer. Take your derivative, you'll see everything matches. 1/2 out in front, you get a minus 4, this to the minus 1/2, then you get a minus 2x as a multiplier, clean that up, and everything matches. Okay, now number 4. Now I'm going to push you a little harder here. And this is where we're going in Chapter 7, everybody. So a little bit of a sneak preview. Again, Chapter 7, more integration, higher levels of integration. And some of those higher levels is just a matter of being clever. And being clever is often just about having enough experience, seeing something before, seeing something similar, and being able to duplicate that work yourself. If you look at this one, this is kind of a combination. If this plus 4 wasn't here, well, we just solved this problem. We literally just did it right here in number 3. If the 8x wasn't here, well, we solved that as a part of problem number 1. But they're both here. So we got a little bit of a problem. This is here, so it's not just inverse sine. This is here, so it's not just a straightforward u sub. But what can we do? We can break this apart. Again, not the first thing you would think of. We are way more often taking multiple fractions, putting them together to make it one fraction. This almost seems counterintuitive, like we're making our life more difficult. Now I have to integrate 2 pieces, but now both pieces work. Now, over here, we've got a u sub that will work. Remember, you try this u sub, and you have 8x plus 4 over a minus 2x, it doesn't cancel anymore. You can't pick and choose how to cancel the x. You have to follow the rules of algebra. So you have some extra addition here. That x would no longer cancel. But now that u sub works, so we've already done this. This is minus 8. And this time I'll just rewrite it as the square root. And that's done. Not, again, not assuming we already did this problem, but we would do this work to just solve this piece. And then this one would be easy, because this one is just inverse sine. Okay, let's try that again. Let's try that with a similar type of problem. Number 5, let's look at the integral, and let's look at 5 minus 9x over 1 plus x squared dx. Now, that denominator has to stand out. That denominator is awfully close to here. But again, experience. These are different looking integrals, but they have a similar situation. If this 9x wasn't here, that is 5 inverse tan x when you take the antiderivative. But we can't ignore that the minus 9x is here. So now, if we go too quickly, and if we don't have good experience, we might jump into a u sub. It's a very natural thing to try here. We've seen plenty of problems like this. That's division. It's not complicated division, but there's nothing I could do to actually divide that. So, and by the way, that does come up. I don't expect you to remember polynomial division, but if the highest exponent on top is bigger than the bottom, then they would expect you to do some polynomial division. Again, we'll get a little reminder of that in, I believe it's 7.4 if I remember correctly, but just a little quick ahead. This is division, and a big reason we can't do anything with this division is because the degree of the denominator is bigger than the degree of the numerator. So, tempted to make a u sub. What could work as u? Well, experience says u as the denominator might be worth a try here. Du would give me a 2x dx, and that temptation to say, hey, look, it's working. That x will cancel with this x. But does it? It actually doesn't, for the exact same reason we were just saying up here. If you try and plug this in, the denominator's u, 5 minus 9x on top, du over 2x, right? Solve that for dx to make that a clean substitution. And these do not cancel. It's tempting. It's really tempting to cross these off. And then, oh, people go 5 minus 9 is minus 4 and minus 4 over 2. That is all garbage, everybody. So once you make that first bogus move, it makes it seem like other good things happen, but that is not a legit cancellation. And since it's not a legit cancellation, this USub wasn't working. But it seems like we've exhausted all possibilities. Well, think about here and think about applying that. What happens if I separate the fractions? Now we're in that same spot. Now over here, this one is ready to go. 5 inverse tangent x. And, again, everybody, just be careful here. That's not inverse tan x squared. It was x squared here. It's plain x here. It was u squared here. It's plain u back over here. So that one was nice and easy. This one's not easy, but now this will work because now it doesn't have that extra multiplier. So now I'll just do this off on the side here. So I've got just minus integral 9x over 1 plus x squared dx. So minus 9x over u du over 2x, right? Using that u substitution. It does work now. Minus 9/2 out in front. 1 over u du. When you pick u as the denominator, you are lining yourself up with this. So unlike here, where we still had to move that u to the numerator in order to use power rule, here, if you do bring that up u to the minus 1, that's where we keep saying maybe you want to put that on your list as well. So you don't use power rule. You realize 1 over u was good. You don't have to rewrite that. That is taking you back to log of u. So this will be minus 9/2. That's pushing out in front. And this would be log of u. And again, a very good answer. The logs, the book loves cleaning them up. Here, 1 plus x squared would definitely already be positive, so parentheses would be appropriate here, but it doesn't hurt to have the absolute value. Here, the 9/2, that could come inside as an exponent, and then you could play with that. This would be the square root of 1 plus x squared all to the 9th power. So there's lots more you could do, but you don't have to. That is more than enough. Okay, so a really good one playing with inverse tangent. Let's still just get a couple more here. Again, this is really just good practice. This does help us prepare for Chapter 6. It's not just integration on our test for Chapter 6, but that's a good chunk. That's quite a big chunk. But again, we're going to need all these things for Chapter 7 as well. So a couple more. Number 6. Let's look at the integral of, let's do x to the 5th, x to the 12th plus 1 dx. We don't have any extra addition subtraction here, but we definitely have an extra variable on top, so we're in a little bit of trouble here. We've got some division here. Degree of the top is already lower than degree of the bottom, so there's no dividing that or anything like that. Well, what can we do? Try u as the denominator. We just tried it in the last one, and it worked. So why not try it here? Well, unfortunately, this one doesn't work. The derivative would give you a 12x to the 11th. Again, if you tried to force that in, this would become your u, du over 12x to the 11th. All of these x's cancel, but you still have 6 x's left down here. And there's no, sometimes there are some clever USubs where you could keep using that U definition to keep manipulating that, but that's not happening here. So again, it was a good try. If this was x to the 11th over x to the 12 plus 1, that would have been a perfect cancel, right? If that was x to the 11th, you would have got a 1/12 log of u plus c, and you'd be done. So it's not that this was worthless. That could have worked if the power in the numerator was a little different. But this didn't work. Again, this all did not work here. So let's get rid of all of it. What else can we try? Well, okay, that was tempting. But now we have to move on and try something else. Let's try this, right? If we look at this, 1 over u squared plus 1. Well, we got to get that to be a 1, but let's focus here. Maybe this will help me to get u. If this has to be u squared, well then plain old u would just be u to x to the 6th power. And now du, that gives me the right power of x. And now I feel much better. Not a bad start, but then hopefully here we start to realize this isn't working. Definitely as we plug in, we realize it's not working. Try something else. But now here, hopefully now we're feeling better. And once I actually plug this in, for the moment the x to the 5th is hanging out. But now here, it's not, this is now just a big u the way it was over here. The whole purpose was that this piece is what motivated our u squared, so the denominator is u squared plus 1. Again, that's not coming from thin air. Everything I've been doing here, once this didn't work, everything I've been doing here is motivated by getting that problem to match this. That's how I pick my u squared. Now I've got the u squared plus 1, feeling good, but don't forget this part. That's another issue in USubs. People ignore the dx. They just magically transform it into du. It doesn't work like that. You got to work to make a dx into a du. But people just magically make it into a du, and they go, oh, it didn't work. But that's not dx became du. Dx became du over 6x to the 5th. Those x's did cancel. Don't let that 6 bother you. That's a 1 over 6 out in front. 1 over u squared plus 1. That is inverse tan of u. And again, just at the end, don't accidentally make that inverse tan u squared. When you back sub, don't plug in the x to the 12th. That's u squared. U is just x to the 6. So I did that one with inverse tangent. Everybody, I can do the exact same trick with inverse sine. So I'm not going to solve this one, but same thing. If you tried u as what's under the radical, you'd end up with this. You get a 12x to the 11, and in the same way, this wouldn't cancel. Here you'd have the square root of u, x to the 5th du over, you would have, this would be 1 minus x to the 12th. So it's just slightly different, but still, overall, same thing happens. You still have a lot of x's left over, so u as the inner piece doesn't work. If this was an x to the 11th on top, that would be your u sub. But now you'd have to try the same thing. It will work, and now it's not u squared is minus x to the 12th. It's just u squared is the x to the 12th. The same thing happens. This would end up becoming this, so you get 1/6 inverse sine of u. And both of these, everybody, take a derivative, right? There's no harm in doing that, especially with the idea of take-home tests. To take an extra minute, take the derivative and confirm, yes, there's no doubt. The derivative here gives me this after I clean it up. The derivative here gives me this after I clean it up. Okay, so 2 more. Didn't really do a lot with E. E is not as bad, right? We've seen a lot of that in the beginning, just getting U as the exponent when it applies. We saw some others where still the E is a part of something inside, so to pick that as your U. So the last 2 I just want to do before we move on. One last little problem to point out, how inverse tan can really, really end up being ugly. So let's call this one number 7. Let's look at the integral of 1 over x squared plus 2x plus 2. You know, again, doesn't seem too bad. You try u as the denominator, you get du as 2x plus 2. There's no x's to cancel. So it feels like you're stuck. But believe it or not, you're supposed to complete the square here. You're in some trouble. By the way, this is just for your information. Even as I talked about, everything up to this point is definitely fair game when we move into chapter 7. It's technically even fair game right now for chapter 6 and that test. But this is really just for your information. If you complete the square here, you go x squared plus 2x plus 1. Already have a leading 1. Cut this in half, square it. That's the missing magic number. But we can't ignore that the plus 2 is here, and this plus 1 can't come from nowhere. We don't have another side of the equation to say, hey, I add 1 on the left, add 1 on the right, so I have to balance that with a minus 1. The point of grouping these together is that this becomes a perfect square. So through that little manipulation, this became this, and this is your u squared plus 1 format. So this would end up being inverse tan of x plus 1. Not obvious, but just pointing out these denominators, little things that we can do to manipulate them, and the fact that this was an x squared, we could work hard to make it a perfect square. It's not just an x anymore, it's an x plus 1 quantity squared, but that's a possibility. And I mean, we could do the same thing with the radical, and you know, if this was 1 minus this, we'd end up with 1 over radical 1 minus x plus 1 quantity squared. So I could do similar things with inverse sine. If this didn't end up being a perfect 1, like if this was a plus 5, well, 5 minus 1 would give me a plus 4. I'd have to pull the 4 out, right? We'd factor a 4 out of this so that this is a 1, and this would be over 4. So now, actually, because it needs to be squared, it would actually be a 2. Because all of this would now be your u squared. So again, we could continue to manipulate. We've already seen if it's not a perfect x squared plus 1, if this was a 16 plus x squared, we could do some little manipulation to make a little u sub work, and it still works out to be a nice inverse tangent. Or if this was, again, a 9 minus x squared, that would eventually work out to be a nice inverse sine. So we've already seen those a little bit, just to see how completing the square can come up. Okay, last one, and this one can come up on this upcoming exam. Like this again, this was a little for your information. This last is a very legitimate problem. Because so far, I've basically been focusing on, you know, the new functions, logs, inverse sine, inverse tangent. But what about this one? Sine theta secant of cosine theta d theta. Looks very ugly. Definitely is not a known trig antiderivative. So we got to work a little bit. There's multiplication, inner, outer. So this actually goes back to our most basic u sub. Where do we pick our u? How do I get started? Well, I've got a messy situation. I'm dealing with both multiplication and inner, outer. So I'll try u as the inner. Du, that's negative sine theta d theta. Hey, that was my choice of u. The derivative cancels with the extra piece. And not a problem if you have to see it on the next line, but just all these good habits that kind of confirm for us a little bit faster as we get more options, as there are more possibilities of what it's going to take to solve an integral. It's great when we can identify, are we making good progress? Is this working? I mentioned way at the beginning of class, a lot of this class, it's nice to have a full answer key. Not just looking at the answers in the back of the book, but being able to look at a step-by-step solution. So I hope you've thought about that. I hope you've searched online. There are a lot that go with the Stewart Calc book. And I think that's important because as we get deeper, these integrals, you may not get the right answer because you made a silly little mistake along the way. So having a full step-by-step solution, you can realize, no, I was making the right USub, something else went wrong along the way. But here, this is working, the sign is there, this became secant of u, d theta became du over negative sine. These cancel. I still do have the extra negative. And now you may feel like, well, I'm stuck. What am I supposed to do with that? But once again, we now have that on our chart. We used to only know the anti of sine and cosine, and the others were, again, very fancy, secant squared, cosecant squared, secant tangent, cosecant cotangent. They were fancy, had combinations, multiplication, inner, outer, but now a plain secant, we now know the answer. That is log of secant u plus tangent u plus c, and I'll back sub secant of cosine theta plus tangent of cosine theta plus c.